All right. So we are going to start with 3.3 today. All right. So that is the next section in your textbook. And notice that this is called part 1. We'll be doing a part 2 after the exam. But one thing to keep in mind about the next few sections is we're going to be using a lot of algebra. And we're going to be computing things, computation. All right, so we're going to be looking at a lot of, oh, shoot, let me pause the video. Okay, so 3.3 part 1, we're going to be looking at using a lot of algebra, a lot more computation. All right, so for some people, this is much more comfortable because it's a little bit less notation that's not as familiar to us. But one thing that I do want us to really keep in mind is that all of what we're doing is rooted in concepts, all right? And the more strong our connection is to the concepts, the easier it will be to choose which technique to use. Okay. And so this is something that I talk to my friends who I do have some friends who are like, I'm just not good at math. I just never knew what rule to use when. And I think there's a lot of folks who feel the same way, that like, there's a lot of rules and how are you going to know when to use them? And I think one thing we really want to keep in mind is the closer we can keep it to the concepts, the closer we can listen to, like when we're in class and we're sharing techniques, like, oh, okay, here, let's use this one because of this, or let's use this other strategy because of that. The more we listen to those conversations and have those conversations on our own, I think the easier it will be to think about, okay, how do I know when to use what? Okay. And so we're going to start as we normally do with our what we know. On Monday, we talked about average versus instantaneous rate of change, and we also talked about the formal definition of a derivative. But I do want to add one more sort of like underlying thing, okay? And this can be something that for some of us, we have a very strong foundation in, and for others of us, we're like, I don't know, I don't remember how to do these things, okay? But regardless of where you are, this is a good reminder to be like, okay, these things are going to be important. And if I want to be successful in this experience, then it would be important to spend some time with them, okay? And so this last bullet point here is our good old friend, algebra, all right? Now, what do I mean by algebra? Some of the concepts that we've already seen, like factoring. Factoring takes you very far. The idea of conjugates. Conjugates takes you pretty far. Our best friend, fractions. Fractions gets all capitals because fractions will take you very far. And that's what I mean when I say algebra. Okay, it could be factoring, it could be conjugates, it could be fractions. All of those are going to be sort of hidden in the work that we're doing. Okay. And so as we move into this next phase of our curriculum, we want to make sure, okay, we're making sure that we feel good about the algebra. All right, but what's new? So what's new? We have a bunch of rules that we're going to learn today. And as we get closer to the next exam, this list is going to grow really, really long. Okay. These 4 are some of the more what we call fundamental rules, and in that we see them pretty often. All right. But I also want to make one thing really clear. These rules are all shortcuts for the formal definition. All right, so the formal definition that we saw on Monday everything that we're learning now is a shortcut for that. Now, some of us who've seen calculus before, power rule, we're like, oh yeah, we know that one. Sum and difference, we know that one. Sometimes we get a little hung up on the product and quotient rule. They can get a little messy, but at the end of the day, no matter how messy a problem is, it is going to be less messy than if I said, I want you to use that formal definition. Okay, so it's almost like a encouragement to think about the glass as half full rather than half empty. Okay, so again, however you feel about all these rules that we're going to learn, maybe they seem really overwhelming, maybe they seem not as bad. At the end of the day, they are better than using the formal definition. Okay. All right, so let's talk a little bit about the concept, a quick review of what a derivative is. Can someone remind me from our conversation on Monday, what is a derivative? I hope that silences us flipping through our notes from Monday to try and refresh our brains. All right. A tangent line at a point. All right. Any other thoughts on what is a derivative? Okay. I'm seeing a lot of really good words here. Slope. All right. All right. Okay. So one thing that we want to be thinking of as we do these is not just like how to do the math we're doing, but also like, what are we even doing? Okay. And so a derivative is something that we want to think of as the slope at any point on a function, right? Is the slope at any point on a function. We can also think of it like the instantaneous rate of change. Okay. So slope at any point on the function, instantaneous rate of change, great. And since we're looking at a single point, this is usually the slope of the tangent line. Okay, so all good words to sort of keep in our brain when someone says, we're finding a derivative. Okay, so let's put a picture here. I don't know why my functions always end up looking the same, but well, we have a function. We're going to call it f of x. Okay. I'm going to draw a few different lines. What's the slope at that point? Yeah, slope at that point is indeed 0. All right, so slope equals 0. Okay. What about this point? How would you describe the slope of that orange point to me? Okay, so you could give a number, that would be okay. What if you were to describe it more generally? What if you were not committed to having an answer as a number? Do we think that slope is negative? Do we think that slope is positive? What do we think? Yeah, and if we sort of sketch a tangent line here, right, we could maybe see that that slope is positive. Okay, I don't know exactly what it is, but it's positive. And maybe we'll do in purple. What if I had this purple point right here? How would we describe the slope at that point? All right, Marilyn says negative. What are our other thoughts? We agree, we disagree. Yeah, this is going to have a negative slope. Okay, I don't know what it is, but I do know that it's going to be negative. And so we could say m is negative. Okay. So some words to think about what a derivative is, some pictures to help support that. But I want to put down a sentence that maybe will frame like what we're going to be doing when we talk about finding derivatives. Okay. So to find the slope of a function at a specific point. Okay, so at a specific point, we first find the derivative of the function. We first find the derivative of the function, then we substitute in the value of the desired. So to find the slope of a function at a specific point, we first find the derivative of the function, and then we substitute in the value of the desired point. Okay. This, even though it's a lot of writing, I think helps us get at what we're going to be doing like once we start finding derivatives and plugging in numbers. Okay. Now, I do want to talk a little bit about notation because there's a lot of different ways to write derivative using math symbols. Every instructor, every textbook is a little bit different. And so I want us to be familiar with all of them so that we can say, okay, no matter what resource I use, no matter who the professor is, when they use the symbol, I know what they mean. All right, so some notation. To write derivative, not using a full word derivative. All right, so to write derivative using math symbols, we have, I would say these are the four most popular ways. Okay. Alexis, that's a great question. Can you use notes on the exam? The short answer is no. No, you may not use notes on the exam, but I will send out more information about ways to prepare for the exam later this week. Okay. All right, so to write the word derivative using math symbols, these are the four most common ways in no particular order. The first way we saw on Monday, f prime of x, all right, f prime of x. And so the way we say that, we say f prime of x, all right? Another way that we can write this is we can say y prime, y prime. Another way we can say this dy dx, right? And we just read this dy dx, all right? Every once in a while, you'll meet a mathematician who says dy over dx, but it's not as frequent. Most folks say dy dx. Okay? I would say these are the top 3 ways. Every once in a while, you'll see something like this, d dx, and next to it, you'll have f of x, okay? And this, we would say d dx of f of x, right? But I feel like primarily these top 3 are the ones that we see most often. Every once in a while, we'll see something like this, but all 4 of those ways mean find the derivative. Okay, so I'm trying to use different notation as we sort of go along in today's notes, but also on like quizzes and things like that, just so we get used to reading all those different ways. Okay. All right, so let's go ahead. We're gonna start with the power rule. That is the first of the rules that we will take a look at today. All right. So we have this example. Example 1 says f of x is x squared, and we would like to find f prime of x. And so there's no words in this question, but using the symbols, right? Using the symbols, I've said find the derivative of f of x. Right? When we see those symbols, that is what we are being asked to do. All right, so f prime of x. The power rule we use when we see a number in the power. We see a 2, okay? We're going to take that power. We're going to bring it down to the front. We keep the variable. And then in the power, we lose 1. Okay. If I simplify this, I get 2x. And that means that my derivative of x squared is 2x. Okay. If we were to write this out in words, this means that the slope at any point on f of x, all right, so the slope at any point on f of x equals x squared is 2x. I want to draw a quick picture. It's not going to be accurate because I don't have a grid here. But if I think about the graph x squared, we have some sort of parabola, okay? And let's pick some points. What's the x value at this pink point? X value is 0, okay? So if I want to find the slope at x equals 0, I'm going to plug 0 in for x into this derivative. So 2 times 0 gives us what? 0, okay. And what is the slope at this pink point here? 0, right? If I were to draw a tangent line, we would get that the slope is 0, okay? Let's say this point is 1, 1, right? Is the slope of that green point positive or negative? Okay, it's positive. So if we think about drawing in that tangent line, it's positive. But you can actually give me a more precise answer now. What is the slope when x equals 1? What is the slope of this green line? How did you get that? Yeah, 2 times 1, the equation for the derivative, 2 times 1, because 1 is the x value, tells me the slope of that tangent line. All right, let's pick a third point. Let's say this point is -2, 4. Is the slope here positive or negative? Nice, right, exactly. This slope is negative. I bet though, we can get a more precise answer. Instead of saying it's negative, since we have the equation of the derivative, we could plug in our x value, right? -2, plug it into this 2x, and Enrique, you are correct. The slope here would be -4. All right, so when we're finding the derivative, all we're doing is finding a function or a formula that tells us the slope of every single point on that original curve. That's pretty powerful. Okay, I could, with this equation, I could give you any x value, even if it's totally off my picture, and you could tell me what the slope is there. All right. But let's go back and think about this power rule. Okay, so I want us to think about the concept, but I also want us to think about like, how do we do this? All right. So can someone describe to me over here, like, what did I do? How did I get from x squared to 2x to the 2 minus 1? What are some things that happened? Okay, that's a formula. I agree with that, but let's describe in words. What happened?
You lost a number in the exponent.
Great, I agree with that. We did lose a number. All right, so up here, we subtract 1 from the power. All right, I like that. I like that. Great, and Raylene said, brought the power down to the front. Exactly, so bring power down as coefficient. Great, great. All right, and that is exactly what this blue box says. Okay, this is exactly what this blue box says, except they use some symbols there, right? Some symbols, and I want to make sure now we know how to read that symbol, right? So in our example, we had a power of 2, but in the definition, they're just saying any number n, okay? N is in the power, and it is exactly what we described. We take the power we bring it down as a coefficient, and then we subtract 1 from the power. That's where we get n minus 1 from, okay? Now this rule is called the power rule, and it explains again in words, all we are doing here is bringing the original exponent down in front and multiplying, and then subtracting 1 from the original exponent, okay? This note, though, is so important, all right? We're not going to really need it again until maybe 3 weeks. However, the earlier we can start to get this in our brains, the less mistakes we're going to make later on, okay? In order to use this formula, all right, so the only time you can use the power rule is n must be a number, okay? N, the power has to be a number. The power cannot be a variable, okay? So we have to have an exponent that is a number, but we also have to have the base as a variable, right? We also have to have a base as a variable. And so one thing, I see a lot of good questions right here. Give me 1 second. One thing I'd like us to write down before we sort of move on to the other practice problems. This power rule only works when we have a variable to a number, okay? So you have to have, do this well, you have to have a number up here in the power, and then your variable has to be the base, okay? So the variable has to be in the base, the number has to be in the exponent. And Jordan, I see a question about what about infinity? Can you clarify that question for me a little bit more? What do you mean by what about infinity?
I actually was thinking the same thing too, but now that you described it with a variable, then would it not work?
Okay. So yeah, is it a number we can use in the exponent? We do not consider infinity to be a number. So that would be a no, we cannot have infinity up here. Okay, so it needs to be, it could be 1,000, it could be 1,000,000, but we actually never get to infinity. So we can't use infinity as the exponent. Okay, great question though, very great question. All right, before we move on to the next rule, let's do some practice problems here. All right, I've tried to choose a variety of problems because I think that it is important for us to see all the special cases, okay? And so these examples are focused on special cases, that is places where students tend to make mistakes, all right? I want us to lead with these so that as we start to move through these questions, we're like very thoughtful about how to use the rule and what sort of algebra tricks might be useful for us, okay? So let's start with example 2, right? So f of x equals x to the 6th. What is f prime of x, right? Without giving me the answer, can someone tell me, without giving me the whole answer, can someone tell me what the first thing I should write down after my equal sign is? Yep, I agree. We bring the 6. Where did we get the 6 from? Oops. We got the 6 from that power, right? So we bring the power down. Great. All right, x. And what is the power for my variable? Great. Now I'm going to be, I know that we all know that 6 minus 1 is 5. Okay. We wouldn't be here if we didn't know that 6 minus 1 is 5. I want to write out 6 minus 1 because for some of the other questions, this process might be more useful. Okay. Final answer, 6x to the 5th. That is our derivative. Okay. What does that mean? If I find what is the slope at x equals 1 on the graph x to the 6th? Yeah, because 6 times 1 to the 5th is 6. Okay, so this tells us the slope at any point on the function x to the 6th. I won't give you any numbers to try, other numbers to try, because I think any number to the 5th gets pretty big pretty fast. But what would be the slope at x equals 0?
Zero.
It would be 0, right? Because 6 times 0 to the 5th is going to be 0. Okay. Yes, Dallas, what's up?
So I had a kind of a basic question. So is a derivative saying the formula to get the slope, or is a derivative the slope?
The derivative gives us the, if we're looking at an equation version of the derivative, this tells us how to find the slope of this.
So essentially, derivative is a process, not a label. Does that make sense? So like the slope you said was 6, but the 6x or the 6x5 to the 5th power is the derivative.
This is the derivative function, but we could
Okay.
also have a derivative picture. Like if we graphed this, this would be a graph of the derivative.
So yeah, that's what I'm saying is like essentially it's a process to get a new function, but once we actually plug in the value that we want, that's the slope.
Yeah.
Okay.
Yeah.
Thank you.
Of course. Thank you for asking. All right, let's actually try example 4 next. Okay. Those of you who had me last semester, I think might be able to answer this question a little bit more readily. But before we do anything, right, we see y equals the square root of x and y prime equals question mark, right? That's the same thing as saying, what is f prime of x? We're just using a different symbol. Okay. Wait, I see a question. Would x equal the slope? No, x is the point on the graph. So like whatever the x value is, that tells us where the point is.
Oh, okay, because when you said you were plugging in 0, and then 0 would be the slope, would that?
Oh, okay. That was probably a bad example because the number we put in happened to be the same as the number we got out.
Uh-huh.
But if we think back to the first version, I said, like, what is the slope at x equals 1? And the slope there was actually 6.
Okay.
So sometimes they're the same, but not always.
Okay.
All right. So if I want to use the power rule, I think back to what I just wrote, which is I need to have a variable and I need to have a number, right? This doesn't look like that. y equals the square root of x. But I would say this is secretly telling us variable to a number. How do I write the square root of x as x to 1 power, to some power? Perfect, perfect, perfect. Okay, so x, oops, y equals x to the 1/2, all right, is the same thing as y equals the square root of x. Okay, I would consider this to be something where I rewrite in a form that is useful, because now I have a variable, which is x, and I have the power as a number, which is 1/2. Okay, let's go over real quick where the 1 and the 2 came from, though, because I think this is really important. This power of x on the inside is 1. And that is where this 1 comes from. Okay. When we say square root, there's secretly a 2 here, which is how we get the 1/2. Okay. This is a great example of algebra, things that we learned at some point how to write. Okay. But if we're trying to focus on the power rule here, right? Power rule says I'm going to bring the power down as a coefficient. So what should be the first thing that I write after the equal sign? Great, power is 1/2, so I bring that power down, right? Just like we did with the 6 in the other problem. Okay. X, I'm going to take the extra time to write it like this, right? So instead of 6 minus 1, I have 1/2 minus 1. One half. What's the power of x? Great. Negative 1/2, right? We have a half, we lose one full thing, we get a negative 1/2, right? This, my friends, this first step, that's the calculus. That's the power rule. Everything else we're writing in this box is going to be algebra. Okay. We're going to rewrite our final answer here as one single fraction. And it'll be 1/2 square root of x. Where did I get this square root of x from?
From the negative 1/2.
This negative 1/2 power. So that's one of those exponent rules that we maybe learned a long time ago. Negative powers means that you can write that term on the other side of the fraction line. So the negative means that it's now on the denominator, and then the 1/2 means that it's your square root. Okay. This, my friends, it tends to be the more common answer on like an answer key or something like that. But also, sometimes this form will be really useful, and sometimes this form will be really useful. So being able to go back and forth between the two forms itself will be useful. Okay. But again, the only line here that is the calculus is this right here. Everything else is just rewriting it to be more convenient. Okay.
Just to understand, if x equals 9, let's say, so the slope would be 1/6.
Yes, exactly. Exactly.
I have a question too. So if it was positive, it would go on the top and there'd be just 2 square root of x.
It would be square root of x over 2.
Okay, then how come you put the 2 at the bottom?
This 2?
No, for 1 over 2, square root of x.
Okay, so 1 over 2 is this 1 over 2.
Mm-hmm.
Okay, then x to the negative 1/2 is the square root of x on the bottom.
Oh, okay, so it's just getting added onto it. Okay.
All right, let's try example 5 before we go back up to example 3. All right, so I would say, I claim that we need to rewrite example 5 before we can do any work. And in particular, we want to write it so that I see a variable to a number. How can I rewrite the function that I'm given? I have negative 3 over x to the 4. All right, I see one guess in there. Negative 3. All right, so we're keeping the negative 3. And x to the 4th on the bottom is like this square root of x on the bottom, right? Where did it come from? X to the negative 4 as like a numerator, okay? Now we can use the power rule. F prime of x equals, what's the first thing I should write after this equal sign?
12.
How'd you get 12?
If we're bringing the negative 4 to the negative 3, you would multiply it, and that would just become a positive 12x to the negative 5.
Perfect. All right. I'm going to break that down a little bit more so we can all see where that comes from, but your thinking is spot on. I'm going to keep the negative 3 in the front. And now I'm going to use power rule on just this part. Okay. So negative 4x to the negative 4 minus 1. All right. Now we can combine things. And we do, in fact, negative 3 times negative 4 gives me a positive 12. And we have x to the negative 5th. Wonderful. All right. How do we write our final answer without a negative exponent?
12 over x to the 5th.
Okay. So I think one option is 12 over x to the 5th. Or what are some other ideas? Like, what else could we write this as?
Could you do 12 times the 5th root of x?
12 times the 5th root of x. All right, what other ideas do we have? I've seen folks do this, 1 over 12x to the 5th. All right. I would say of the 3 things we've written down, only one of them is correct. What's wrong with this?
The 12 is positive, not negative. Should it be on top?
Okay. What's the power for the 12?
1.
Yeah. The power here is 1. 1 is positive. So I have to keep that in the numerator. Okay. So this is incorrect because the negative 5 is not an exponent for the 12. Okay. why is this part incorrect? This is a really common misconception. Okay. This is secretly saying x to the 1/5. But that's not what this says. This says -5. So -5 is not the same as 1/5, right? So if we want to use a square root, we usually have a fraction in the power, right? And so that does mean that our initial thought is indeed the one correct answer here. Yes, Dallas, what's up?
So I had a question. Why couldn't you do the power rule for the x to the 4th?
That's a great question. Great question. Let's go back and look at this definition. All right. The only time we can use the power rule is it has to look like this. We can think about this as a fraction, but it's 1 is the denominator. And if we go back to this question, x to the 4th is not in the numerator. All right. We have to make sure that we're honoring the fact that this has a negative exponent.
Okay.
Okay. In other words, we want to rewrite it so it literally has a variable to a number and everything over 1. So we don't want any fractions, which is why we sort of have to go through this messiness of rewriting things before we can answer a question. Okay. All right. Well, let's take a look at example 3 here. Yet another notation, right? D dx of pi. I want to take this derivative. What's the first thing that I'm going to write? Or would it be helpful for us to rewrite it first? What's our function that we're trying to take a derivative of? Okay, so the function we're trying to take a derivative of here is pi. If I wanted to write this so I could see my variable, what's the power for the variable? All right, so x to the first power is pi the same as pi times x to the first power? What do we think? Is pi the same thing as pi times x? No, okay. So what is the exponent for the x then? I agree, it is indeed 0. Okay. Now I see my power. Now I have my variable to a number. Now I can use power. So if I were to use power rule, what would be the first thing that I write down after the equal sign? Okay, I say almost, because we still have this pi here. We only want to use the power rule on this part. So 0, x to the 0 minus 1. equals, let's see, pi times 0 times anything is 0, which gives us 0.
Professor, I have a question. You kind of lost me. So every single example has been saying like f to the prime of something. This one you had to do it the opposite, like you had to show the function.
So sometimes you get the function inside the parentheses,
Mhm.
which is just a different way of asking it. So like I could have written example 2 like this. I could say dx of x to the 6th.
Oh, that's right. You just went over that. Sorry, my bad.
You're fine. I'm throwing so much content at you all right now. It is
I was
totally,
like, hold on, whoa,
Yeah.
what are we doing here? Okay.
yeah. All right. Now, I'm wondering though, because we haven't gotten an answer of 0 out yet, if we were to draw a little picture of the function pi, what does that function look like? Yeah, I agree. It's a horizontal line. In fact, we might even say that it's a horizontal line. This is at y equals pi. What's the slope of that line? 0. Guess what our derivative was? 0. Because the slope everywhere on this line is 0. Okay. What do you think if I said y equals 1/2? What would the derivative of that be? Indeed, a horizontal line at y equals 1/2 will always have a slope of 0. Okay. What about y equals negative 101 over 2? What is the derivative?
Still 0.
Still 0, because we still have a horizontal line. Right? What if I said y equals 2x? What's y prime going to be?
Still the same.
What do you mean by the same? Like it's going to be 0? All right, Raylene, 2. What's y equals 2x? What's that look like? Yeah, just y equals 2x. Think back to your middle school, high school days, and someone was like, graph that y equals 2x, and you got a line. Slope of that line is 2. Derivative is going to be 2. Just something to think about. But let's take a look at example 6. Then we'll take a break and then come back and talk a little bit more about those special cases. Okay. All right. Example 6. Can we use our power rule in the form that it is, or do we have to rewrite something?
Definitely rewrite.
Definitely rewrite. All right. What is a better way to rewrite this? Well, I would maybe take it step by step, right? I would keep the 2 up here, but what's a different way that I can write the cube root of x squared? I wanted x to a power. Okay, and it might be helpful to think about our previous example with the square root of x and how we wrote that. All right. So let's see, the number on the inside. So there's a 2. Number on the outside is 3. All right. So when I had the square root of x, it was the inside power as the numerator and the outside power as the denominator. So that's how we got 1/2. And I would agree that over here we have the inside power as the numerator over the, we call that the root on the outside. Okay. All right. This is almost there, but sort of gets to what Dallas was asking earlier, like how come we can't just use our power rule from here? And my not so great answer was basically because we need to have it with a denominator of 1. And so how would I rewrite this so that I would have the x to the 2/3 in the numerator?
Just put a negative sign in front of it.
Yeah, so 2x to the negative 2/3. Okay. If you struggle with rewriting things like this, I would encourage you to break it up into 2 steps, sort of, take care of the radical first and then take care of the negative sign. But once you have it like that, now we can use our power rule. And in fact, the first thing that I should write down is not going to be negative 2/3, but it's going to be 2. Then I bring down the power as a coefficient, and then I lose a power in the exponent. Okay. What do I get when I combine these coefficients here?
Negative 4/3.
Perfect. Negative 4/3 x to the negative 5/3, right? So here's a little bit of that fraction piece, right? We want to make sure we know how to add and subtract fractions. We get x to the negative 5/3. All right. Now I want to pack my answer back up to look like the way the question was asked. Let me do this step by step. I'm going to keep my 4 in the numerator, but the 3 goes in the denominator because 4/3. And if I move this x to the negative 5/3 to the bottom, I get x to the positive 5/3. And then my last step is now to turn this back into a radical. I'm going to put the 5 in the inside and a little 3 on the outside. Okay.
Should
So
we always do exactly what the function originally asked us for? Like put our answer that way?
yeah, that's a really good way to approach things. If you get asked the question in a certain way, make sure you answer it in that certain way. Okay. All right, Dallas, what's up?
So I had a question about why you multiply the number that pretty much jumps down in front of the x for these types of problems, but not the example that's right above example 6. Because, yeah, I think you did one of them where that would essentially turn into 0, but then, or for the 2x, if you did the power rule, that would make x into 0. And then, like, I guess, why didn't you multiply 2 by x or 2 by 0?
Ah, okay. So that's actually a great question. Let me sort of finish this down here. If we had y equals 2x and we were to use the power rule, the power here is 1, right? So y prime would be 2 times 1 x to the 1 minus 1, which is 2. 2 times 1 is 2, x to the 0, which is 2.
But isn't anything to the 0 exponent 0?
No, anything to the 0 exponent is 1.
Oh, okay. Good. That's where I was confused then.
Okay. Yeah, that's why we were able to sneak in this x to the 0 here. Because it's pi times 1, and our way of saying 1 is x to the 0.
I was confused on that too, like with the same thing that he was saying, but then when you did that x to the 0, also known as 1, you wanted a variable to the exponent. So I was like, oh, okay.
Yeah, exactly. So this page is 5 examples, but it's very dense in terms of what do we do when there's a fraction? What do we do when there's a negative exponent? What do we do when there's a fraction and a negative exponent? What do we do when we don't even see a variable, right? So I would encourage you to look up some other examples that are kind of like this. If you feel like any one of those was sort of trickier for you than the others, go find some examples. And in fact, I'll leave you with this before we take a break. So on Monday, I had said that there was sort of a place where I'm getting these ones with the blue highlighting in the background. So find the website. I'm gonna drop this link in the chat. This would probably be a good thing to bookmark. But this is Paul's online notes. If you're looking to take Calc 1, Calc 2, Calc 3, differential equations, he has so many resources on things. This might be a great study tool for the exam, but in particular, let me see if I can share the screen real quick. Can you folks see that? Yeah, okay, great. So let's say you want to practice later on. All right, he's got examples here. And the best part is you click show solution and he shows you his steps, but he also talks you through his steps. So right here we have 1, 2, 3, 4, 5 practice problems. There's another 2 practice problems down here. There's a 3rd one, a 4th one, a 5th one. And if you're like, I did all of those and I want more practice, you can go up here to the tab that says practice problems. Click on that and he's got 20 practice problems. Each one comes with a solution, all right? But here's the cool thing. You can show the solution, all right? Well, this is a bad example, but let's try maybe this one. You show your solution, he shows you the little steps in between, all right? But for some of the more complicated problems that we'll take a look at, he actually shows like, just show me the next step. Just show me the next step. So you can choose to show the whole solution, or you can just show it step by step. But he has a bunch of practice problems. You can go back and look at all his ones for limits. That might be helpful for studying for the exam next week. Okay. So I'm going to stop sharing that for a moment. We're going to. All right, so 2 special cases of the product rule. So we're going to divide this page in half. We will talk about the constant rule first. Okay. Now, the constant rule is something that you'll sometimes see in textbooks as like a different rule. I like to think of it more as a special case of the power rule, but it is important to sort of talk about. So suppose we take a derivative. So let's use this notation, the d dx. And inside the function that I'm looking to take the derivative of, I just have a number. Okay, so this c is a constant. And so we actually saw an example like this above. Does anybody remember what we had in place of c?
Pi.
Yeah, we had pi, right? So d dx of a constant, no matter what that constant is, as long as it's just a constant, is going to be 0. Okay. The reason for this, we can say, since y equals c is a horizontal line, the derivative, oh, sorry, not the derivative, the slope will be 0 for all values of x, right? Therefore, the derivative is 0. Okay, so since y equals c is a horizontal line, the slope will be 0 for all values of x. Therefore, the derivative is 0. Okay, when you have just a number, it's not attached to anything else. It's literally just a number. Okay. So some textbooks consider that a separate rule, and however that fits best in your brain is fine. Another common rule that folks sort of give it its own name is the linear rule. Okay. And the linear rule is a slight modification. It looks like d dx, and inside, instead of just a c, we have cx, right? So cx, kind of like that 2x example. We had a number and then we had x. See here, just a number. And this x is x to the first power. Okay. And anytime we have that, all right, if we were to graph cx, we would get just a line. And that line has the same slope everywhere. In fact, it has a slope of c. And so that's why when we take the derivative of something like cx, we're always going to get c. And so if we write that out in words, similar to we did before, we can say, since cx is a linear function, okay, meaning it's just a line, with a slope of c at every x value, the derivative of cx is c. Okay, so the rules that you'll see in a book probably look like this, but the things in the blue here are hopefully helpful in like understanding why those rules are the way they are. Okay. All right. Let's go ahead and take a look at the sum and difference rules pretty quickly. So it turns out that derivatives, when we add and subtract things, work exactly the way that we want them to. Meaning, if I have a bunch of things connected by pluses and minuses, you just take the derivative of each part and then put the pluses and minuses in between there. Okay, so this will be a nice way to sort of string together some of the questions that we looked at on the previous page. All right, so let's take a look at example number 7. All right, so we have y equals x to the 8th plus the 5th root of x squared minus 5 over x. And the question is find y prime. All right, and so my suggestion for these questions would be always to start by rewriting. Okay, rewrite it so that in every single place you can see the variable to a number, variable to a number, okay? Now, some of the terms you don't have to rewrite, like x to the 8th is fine. I can leave it like that, x to the 8th. Plus, what's the power for this second term, the one with the radical? Yeah, is it 2/5 or 5/2? That is a good question to ask ourselves. All right, so let's see. The number on the inside is 2. The number in the root is 5. And so indeed, we have 2/5. Okay. Minus the last one here. How might I write this last term instead of 5/x? How can I write that without a fraction? Great, 5 times x to the -1. And if you feel like you tend to make this mistake, you might even want to put a +1 as the exponent for 5. Okay. But now that you've rewritten it, right? So you did the algebra. Now we're going to go ahead and find y prime, right? So power rule for each step. And because this is still sort of our first day of doing derivatives, I'm going to write out like all the extra steps, right? So for x to the 8th, it's 8x to the 8 minus 1. Right? Again, I know we know that 8 minus 1 is 7, but in case we forget what the pattern is, that's helpful. Plus 2/5 x to the 2/5 minus 1 minus 5 times -1 x to the -1 minus 1. All right, so showing every single step. And now, like that's the calculus. Now we simplify. Okay, so I get 8x to the 7th plus 2/5 x to the -3/5 plus 5x to the -2. All right. And as was suggested earlier, it's good practice to put your answer in the same form that the question was asked. So that would mean no more negative exponents over here, no more negative exponents or fraction exponents here. All right. The numerator for the second term is going to be 2/5. So again, this 2/5 represents the 2/5 coefficient. And underneath where the 5 is, we're going to have x to the 3 and then the 5th root of that. How do I write the last term here? 5x to the -2.
Five over x squared.
5/x². You got it. All right. And so this complicated looking equation tells you how to find the slope at any x value of this original function. All right. So yes, we're doing a lot of computation, but what does it mean? This anywhere, if I plug in any x value, it will tell me the slope of this original function. Okay. All right. I will leave you to do example 8 as optional practice on your own time. Again, this is a great one if you're like, I tried it on my own, I didn't really get it. Can we go over it in office hours? We can totally do that. Okay. All right. So the second chunk of class, we're going to talk about the product rule. All right. The product rule is one of the, probably the second most common one after the power rule. Okay. So when I say product, what math operation do you think of? Exactly. When we think product, okay, when we think product, we're really saying use this when multiplying two functions. Okay. So when we are multiplying two functions, that would be the key word here, right? So the word product should clue us to say, oh, if I'm multiplying two functions, I might want to use this product rule. Okay. All right. So we're going to take a look at example 9, and we're actually going to solve it in two different ways. Okay. We can actually do this problem without knowing the product rule, but we can also use it to practice this idea of the product rule. Okay. So what is another way, maybe one that uses less ink? Yeah, general form would be f of x equals g of x times h of x for sure. What's a way to write x to the third times x to the fourth using less ink?
X to the 7th.
How are we getting x to the 7th?
When you're multiplying exponents, you add them together.
Great. So x to the 3 plus 4 gives you x to the 7th. Wonderful. How would I get x to the 12th out? Using the exponents 3 and 4. Like, how could I change the original question so that at the end I actually had x to the 12th?
Multiply the exponents.
Yeah, exactly. So if I had x to the 3rd to the 4th, then I would be multiplying them. Okay. But when I see the variable more than one time, I'm adding exponents. All right. All right. So we rewrote it. Turns out it's just x to the 7th. Second step, find dy dx. Dy dx equals, what do we get when we take the derivative of x to the 7th?
7x6. X to the 6th, sorry.
X to the 6th. Perfect. That's it. Okay. This problem, not hard to do when you simplify, right? The product rule is going to look longer for this problem, but the product rule will also allow us to handle two functions being multiplied together when we cannot simplify them. All right. So eventually we're going to get to cases, and by eventually, I mean like 2 weeks from now, we're going to get to cases where we can't just simplify it. And then we will be forced to use product rule. Okay. All right. So product rule. In the blue, if two functions, f and g, are differentiable, all right, then the product is differentiable, meaning that you can find a derivative. So if you can find a derivative, all right, this is one version of the rule. So you have two things multiplied and you want to find the derivative. You take the derivative of the first one times the second one. We didn't do anything to the second one yet. Plus the first function times the derivative of the second. Okay. And so what I like to do is make sure I set up my product rule so I know what I'm going to plug in where. Okay. Now, this gentleman, Paul, does his F and G notation. Some people call the functions U and V only because sometimes we already use F here. That's it. Okay. So the work that I'm going to show here is going to have the letters U and V, but they're going to be like this F and G. Okay. So let U equal X cubed. That was the first function. And V equal X to the fourth. That was the second function, right? In the question, we had X to the third times X to the fourth. So I said the first one is X to the third, the second one is X to the fourth. What is du? So what is the derivative of u?
3x to the square.
Yeah, 3x squared. Exactly. I know what you mean. I know what you mean. All right. What do we get for dv? All right. So we have v function is x to the fourth. What do we get for dv?
4x cubed.
Nice. 4x cubed. All right. So this is sort of our setup. Okay. Now, dy dx, the derivative of the function we're looking for. We take, let's see if we can modify this rule from Paul's online notes. Instead of f prime, what should we write?
U prime,
Yeah, u prime, or we called it du. Okay.
or yeah, sorry, du.
Yeah, no, that's fine. So du.
I have a question.
Yeah, what's up?
Where did you get the exponents for the du and the dv?
We use the power rule, right? Derivative of x cubed, you bring the power down, 3.
But
X.
wouldn't x just be the 1 instead of 2?
Well, we lose 1 from the power. So what's 3 minus 1?
2.
Yeah, that's where we get that 2 from.
Okay.
Yeah, and we did the same thing over here. 4 minus 1 gives us 3.
Okay, I got it. Thank you.
All right. So we have du. That's in place of the f prime. What do we write in place of the g? V. Okay. So du times v plus u times dv. Okay. So all we've done is sort of match letters with what we have here. And now we get to plug in all the things that we set up. So instead of du, we have 3x squared. Instead of v, we have x to the fourth. Plus, instead of u, we have x cubed. Instead of dv, we have 4x cubed. All right. Well, let's simplify. 3x squared times x to the fourth gives me 3x to the sixth plus x cubed times 4x cubed gives me 4x to the sixth. How many x to the sixth do we have altogether? We have 7x to the sixth, which is exactly the same answer we got on the other side. All right. I wanted to show you this so that we could see how the product rule works, but you can also approach this question by simplifying first. So like simplifying first can get you pretty far. Okay.
Professor, would it always be the case, like, my mind's just curious, like, what if it was 4x to the 5th, and then now we're back to the sum and difference rule? Or am I like overthinking this?
Oh, like over here, like what if they don't
Yeah,
combine?
like what if they don't match?
They might not match. They might
Okay,
not. Okay, but they would match in the sense that whatever question you did this way should match your answer when you do it a different way.
got it. Okay.
All right. I think for the sake of time, I'm going to skip this proof, okay? But for those of you who might be curious, this does use the formal definition of the derivative, right? Formal definition of the derivative and clever algebra to prove this, okay? If that is something you are curious about walking through, there are definitely videos out there, but if that's something you want to walk through during office hours, we can definitely do that there, right? Sometimes some people are like, just give me the formula, I'm good to go. And other people are like, but I'd really be curious about how we got that formula, okay? But let's take a look at this example. All right, so let's take a look at example 10. I'm trying to throw a lot of different words at you here on purpose, all right? But this word differentiate is another way of saying find the derivative. Okay, when you see that word differentiate, it's different than the way we use it in English, but rather it means to find the derivative. Okay. Now, if I wanted to solve this, find the derivative, okay, knowing that we're in a section for product rule, all right, let's use the product rule here, okay? Product rule says that f prime of x will be du times v plus u times dv. Right? Let's go ahead and set things up. Set things up meaning our u is this cube root of x minus 1. Our v is 2x minus x squared. And we also want to find our du and our dv. Okay. Let's start with the dv. I think that one is a little bit more accessible. What's the derivative of 2x? 2. All right, so the derivative of 2x is 2. This is that sum and difference rule, right? I can just bring the minus sign down. What's the derivative of x squared? It is indeed 2x, right? So using some of the rules we already learned today on finding that derivative. I would say though, before we do finding du, we should probably rewrite that. Right? And so in fact, we rewrite that and we get x to the 1/3 minus 1. Now, what is our du?
Be 1/3 x to the negative 2/3.
And what's the derivative of 1? Just 1. Yeah. Okay. I want to pause here for a moment and make sure we all see what just happened. So we took the derivative of x to the 1/3 and we got this part. But sum and difference rule says that we can just write down the sign in between and then take the derivative of 1. 1 is just a constant, so that derivative is 0. Okay. All right. Just for some good practice, if I were to write this as a single fraction, I would get 1/3 times the cube root of x squared. Okay. Yes, Nora, what's up?
So constants are always 0.
If it's only a constant, like if the term itself is just a constant.
Okay, great.
Okay. Now that we have our setup, let's go ahead and use product rule. Right. And so we're going to get, let's see, du, which is 1/3, the cube root of x squared, times v, which is 2x minus x squared, plus u, which is the cube root of x minus 1, times dv, which is 2 minus 2x. Okay. So this is our du, our v, our u, and our dv. All right. Now, as far as simplifying this, all right, this is actually fine. There's not a ton that I really am looking for you to simplify in this problem. Rather, more of what I'm hoping to see correct is the setup. Okay. This is one of the reasons why I stopped using things like WebAssign or, other platforms like that for calculus, because I feel like sometimes they want you to simplify so much that maybe you had the right answer somewhere along the way, but you're just typing it in a form that they didn't want. Okay. So focus more on this setup. Make sure you know the reasoning for everything and then plug it in. And beyond that, maybe like if there's very obvious like terms or something like that, you can combine them, but otherwise you can sort of leave it. Okay. All right. Any questions on example 10? Okay. Now, you'll notice here that I have a special case of the product rule. And I actually wanted to do examples 11 first to see why this rule is the way it is. Okay. So let's imagine there's no rule up there. I just want you to find the derivative of 5x. What is this derivative?
Five.
Yeah. Why is it 5?
X to the power of 1, 1 times 5, and then x to the 0 is 1, so 5 times 1 is 5.
Good. Okay. So we could say that this is 5 because method 1, we have, how do I write this? The derivative of that, we can take the 5 out and then just take the derivative of x, which gives you 5 times 1x to the 1 minus 1, which gives you 5. Okay, so that's one way that we can approach this question. Why I wrote down the page. So this is one way that we can approach this. Another way, maybe you're clever and you're like, 5x, isn't that just a line, Judy? And isn't that just a line with a slope of 5, right? That's another way to look at it. But let's say you are in the zone and you're like, I don't know, we just learned about this product rule and I really want to try using the product rule because it's 5 times x. Okay. And I would say, sure, let's try it out and see what happens. Okay. So we do a setup. What is our u in this case? And what is our v?
Five and x.
Exactly, right? So 5 is u and x is v. All right. What is your du and what is your dv?
The du is 0
Yes, because it's
because
just.
it's a constant,
Mhm.
but also so is x. No, x is a variable.
Mhm. And again, maybe this is where like sometimes writing those extra numbers helps us a little.
Yeah, I did. In my head, I just did that. And
Yeah, all right. Fatima, looks like you have x, the derivative of x is 1, exactly. We bring down that power and we end up with 1 times x to the power of 0, which is 1. All right, so now we plug everything into the product rule and we get du times v plus u times dv. We plug that in, we get 0 times x plus 5 times 1, and we get 5. Okay. Now, I really like what Enrique said when he was answering, like, how do you find du? Because u is a number, right? U is a number. So anytime I take that derivative, it's going to be 0. And look at what happens. I'm always going to take du and multiply it by v. But that means I'm always going to have 0 times something, which means this is going to go to 0 and we're only left with that last part. Okay. So the way we say this mathematically is if you have a constant times a function, so like 5x, and you want to take the derivative, you bring the 5 out to the front, and then you take the derivative of the rest. Okay. I wanted to highlight that because sometimes, and I'll write this in red, sometimes students look at this question and they say, oh, I only showed up to the first day of class or first half of class that day. And we learned that the derivative of 5 is 0. And the derivative of x is 1. So 0 times 1 gives you 0. Okay. For the student who was unable to stay for the second half of class, what did they miss? What made them make this mistake? Okay, the product rule. I agree, they could use the product rule, but also this 5, sometimes people think, oh, the derivative of 5 is 0, so then everything else is 0, right? But it's 5x, it's not just 5, right? It's attached to something else, and specifically it's attached to a variable. All right. So yes, that would be a great sign to use the linear rule or the product rule, but we don't want to just pretend like we can just split them and then multiply at the end. Okay. All right. let's take a look at example 12. This actually looks a lot like one of the previous examples we had. I just want to make it really obvious to us that the 2 here is the constant. So I can actually write this as d dx of 2x to the negative 9. That make it more obvious. Now 2 is our c. So we bring the 2 out. 2, the derivative of x to the negative 9. We get 2 times negative 9x to the negative 10, because I'm losing one more. And this should give me negative 18 over x to the 10th. Okay. 11 and 12, I secretly made you do those earlier already. All right, but we just sort of talked about them in different ways. But I think it is, again, important to note this is a special case of the product rule. All right, so you could use product rule, or if you remember that special case, it might make it a little bit easier. Okay.
Would you ever throw like a curveball and like, I mean, not a curveball, like on the exam, like show me 2 methods?
Absolutely.
Okay. Because I was thinking, I'm like, can you do that for 12? But when you did that, I was like, oh, never mind.
Yeah. I think like it could be, you know, like example 9, right?
Yeah.
With 2 ways. The nice thing about that, which is why I try to think about it less like a curveball, I know you folks know how to do this.
Mhm.
That also means you know what this answer should be. Right? So it's almost like you make yourself the answer key, and then this is just a longer way to get to the same answer.
Yeah.
Yeah.
Thank you.
Of course. All right. How are we doing? It's 11:40. Great. All right. The last thing that I wanted to talk about today is this quotient rule. All right. So just like when we multiply things, we can also divide things, and they have a special rule. We're going to take a look at this example. Okay. Now, just like was just asked, sometimes there's more than one way to solve it, but eventually we might get to a case where we are forced to use one method. Okay. So let's take a look at example 13. All right, we have y equals 3x squared plus 2x over x. And we want to solve this with 2 different methods. And so we're going to use what we know about algebra first to sort of rewrite this question. But I think this is a little skill that maybe we forget about. So I'm wondering if you can tell me how do I want to say this? 1 over 7 plus 2 over 7. What does that give us?
3 7s.
3 7s, right? Yeah, exactly, right? But how did you get 3 7s?
The denominator is the same, so whatever's on top. So basically what you're going to do is split up the 3x squared over x plus 2x over x.
Okay. So we usually go in this direction, right? You're always asked, like, add some fractions, make it into one fraction. But what's really hidden there is sometimes when you have one fraction, you can unpack it into more than one fraction, right? So that is precisely what we're going to do with this question. And I believe what you said was 3x squared over x, that's one fraction, plus 2x over x. Okay. Now, why would we want to do this? Let's keep simplifying. What does 3x squared over x give us?
3x.
Exactly. This gives us 3x plus, what does 2x over x give us?
2.
Okay. Now this if you want to, I'll show you in a little bit how we can use quotient rule, but I bet you know how to take this derivative. What is the derivative of 3x? Mhm. It is indeed 3. Yeah. What is the derivative of 2? 0, precisely. Okay. This gives us 3. Also, the slope of this line, 3x plus 2, is 3, right? Where this line crosses the y-axis doesn't actually change the slope. The slope is changed by the number, the coefficient of the x, right? That's why the 3 stays, but the 2, that derivative goes to 0. Okay. All right, so then we get a final answer, dy dx equals 3. Great. Let's try the quotient rule. Okay. So again, we've got a little rule down here, right? We're using the letters F and G, but like before, we're going to use U and V, only because sometimes functions are already called F or already called G. Okay. So if we have F, I'm going to take its derivative, multiply it by the bottom. Right? Then I'm going to take just the top and multiply it by the derivative of the bottom. And I'm going to put that all over the denominator square. Let's set up our quotient rule and then make sure that we can figure out how to rewrite this formula and think about what goes where, because the placement of things is really important here. So set up U in this case and V, all right? What would the U be in this case?
Three x squared over x.
Go back to the original, all right? That's a good guess, but in this case, F represents the entire numerator.
Oh, the entire top. Okay. 3x squared plus 2x.
Good. So 3x squared plus 2x. And V is our entire denominator,
Oh, okay.
which is x. Okay. So denominator, numerator. All right. Let's find our du and let's find our dv. All right. When I take the derivative of 3x squared, just the 3x squared part, what do I get?
Six x.
And when I take just the derivative of 2x, I get 2. Perfect. All right. Derivative of x for our dv.
One.
Just 1. Okay. So now we'll put this into the quotient, because quotient means divide, just like product means multiply. So if I were trying to find my dy dx, right, let's match up with this rule here. In the rule, they had f prime first. So what should be the first thing in my numerator up here?
du.
Good. So we're going to have du times v, just the denominator. Okay. So we have du times v minus u times dv. All over the denominator squared. Right? So let's go ahead and plug in what we got. We get 6x plus 2 times x minus 3x squared plus 2x times 1 all over x squared. Okay. All right, let's simplify. 6x squared plus 2x. Where did I get that from? 6x squared plus 2x.
You're just multiplying the x to both items in the parentheses.
Exactly. We're distributing here, right?
There you go, distributing.
All right, minus 3x squared plus 2x all over x squared. What mistake did I make?
You put a positive 2x when you need to distribute the -1 to make it a negative 2x.
Negative, negative, exactly. Right, so we want to make sure that is indeed a negative sign. All right. And now we combine some terms. Look at this, 2x and negative 2x go away. And on the top, I have 6x squared minus 3x squared. Well, that gives me 3x squared over x squared. Those I can reduce because x squared divided by x squared is 1. I know that was a long problem, but if we look back at the other side of the notes, we also got 3. Okay.
So basically, if we were taking an exam and you said show 2 methods and you got the first one and then the second one you didn't get that number, you know you messed up.
Yeah. Yeah.
Okay.
And that's a good place to be like, did I make a sign mistake? Did I write the formula correctly? Did I get things in the right order? Yeah. Okay. I think the last thing that I want to say here, let's see. Okay. All right. So I know that there's a lot of memorizing in terms of formulas, right? We learned the product rule, we learned so many rules today, and now we're learning the quotient rule. I think traditionally the quotient rule is sort of the hardest one to to remember. And so once upon a time, I had someone show me this. They called this the high function because it's above, and this one the low function because it is on the bottom, on the lower part, right? So instead of using like U and V or F and G, they were like the high is the one on the numerator and the low is the one in the denominator. And when they use the quotient rule, they ended up with something like this: low d high minus high d low over low squared. Or if any of you have a low-low. A little tribute to your low-low. All right, so I think this is just more fun to say. Low D high minus high D low over low low, right? It just, sometimes we need a little fun in our lives, right? So if that form works a little better for you, that's fine. What I also really like about this is that the high is the F, right? It is the one on the top. There's no question about it. High means it's the one function on the top. Low means the function in the denominator, right? More boring, but just to write out like our U over V situation, sometimes people say V du minus U dV over V squared. But again, it's just same idea here, just different letters. All right, so whatever way sticks a little better for you, that's fine with me, okay? All right.
And then also too, the top part is the same as a product rule, just a plus sign.
Yes, that is actually very, very true. Okay, so this right here, if we put a plus and we got rid of this, you would have, okay. And I think that's actually a really great strategy overall. Sometimes when we think about memorizing things one at a time, it can feel so overwhelming. But if you're like, I know my product rule, and I know if I change that to a minus sign and put it over V squared, I'm going to get the product or the quotient rule, then you've almost gotten a 2-in-1, right? You've memorized one thing, but it helped you get to another. All right, so I think we're going to stop there. The last two things on here are examples, all right? I would focus more on the setup and less about simplifying, all right? These two questions are designed so that I'm looking for things like, do you know how to take the derivative of a square root? Do you know how to use your power rule for each individual term? Do you know how to use your sum and difference rule? Okay, but at the end, I would not simplify the answer too much. All right, I would almost just get it to the point where you can plug things into the formula, and that's good. Okay.
Sorry, our examples 14 and 15, those are quotient rules, right? Because it's divided.
Exactly.
Okay, I was really overthinking right now. I was like, what?
It looks
yeah.
scarier in this concept. Exactly. These
Yeah.
are quotient rule because we see that divide.
Division. Okay, perfect.
Okay. All right. So my friends, today has been a long day of a lot of things, but we will stop there. Let me go ahead and stop that